Getting fat is a normal process for many animals, and they do it to protect themselves during times when food is not around. So what's really interesting is officially, people who are overweight are high energy individuals. It's just all the energy is in their fat and their active energy is low. When that's low, that's why they're fatigued. They don't want to move as much. Their resting metabolism is low. It's a trick. You're increasing your energy in the whole body because the body has tricked you into thinking that you're in a low energy state. So you eat more, but the energy you're eating is going to the wrong place. So what's neat about allulose is it's sweet, but it's not as sweet as sugar. It looks like fructose, but it doesn't activate the switch. But what's cool about it is that it stimulates GLP-1. If you're using it for weight loss, it makes sense to take it before the meal, and it may actually dampen how much you eat. It is very, very, very noticeable that the allulose can block that postprandial rise in glucose. It's really fantastic. And we've linked that with things like Alzheimer's and other diseases. The whole thing is linked with nature, and it was supposed to be good. It's just that we've learned how to keep it activated at a big level.
Rick, let's open up talking about this fat storage switch that we all have, for better or worse, as human beings.
Yes, our research led to the discovery that there's a switch that actually turns on this obesity switch that turns on this process in which we will gain weight and become fat. And normally animals, including humans, regulate their weight pretty well. And, if you eat more one day, you eat less the next. If you exercise more one day, you'll eat more food to keep up with it. Basically, animals will maintain their weight at a very tight level because they don't want to get fat, because if they get too fat, a predator will get them. And if they get too skinny, they're at risk of starvation. So they maintain their weight. It's a very carefully balanced program. And I was just up in Alaska just a couple of days ago, where I saw all these bears eating salmon, and they were eating huge amounts of fish. They were just pulling one up after another. It looked wonderful. But they weren't getting fat. They're actually fairly lean during the summer. And so they're able to maintain their energy balance. They can use the protein to increase their muscle mass, but they're not really changing their fat stores. But, in the fall, when it starts to get cold and they realize winter is coming, they suddenly change their behavior, and they know that they need to store fat in order to survive the winter. And they start eating very, very dramatically, where they can eat, so much that they gain 10 pounds a day. And there's even a contest called the Fat Bear Contest that's held every year for people who can take a photo of the fattest bear, because in the fall they can get really fat. And they need that, because when winter comes, they hibernate in a little den. And during that time, they don't eat, and they don't poop, and they don't pee, and they just live off their fat. And the fat provides calories that they use to keep them going. And the fat also, when it's broken down, gives them water. So they don't drink water because they get it from breaking down the fat. Water is not in fat, but when you break it down metabolically, you actually generate water. It's called metabolic water. So what our group discovered was that this switch, where the animals suddenly start eating more, is actually a biologically driven switch. They actually activate a process where they become hungry and want to eat more. And we then showed that that is actually the same switch that goes on in us, and we're activating it all the time. But we're not hibernating to burn off the fat. So a lot of us just keep getting fatter and fatter. And the switch turned out to be a very interesting process, because typically it was thought that the way you get fat is you just eat more than you need, and that extra food gets shifted into fat. And the theory is that the energy we use is called ATP, and that energy comes from We produce it when we eat food. So when you eat food, you're producing this ATP, which is how we do everything we do. So ATP is like the critical thing that we're making. And this gives us the energy to do what we want. And it comes from there's factories in our cells that make this ATP from the food we eat. So when we eat the food, the factories turn on and produce ATP. And the theory was that if the ATP levels are high, that there's no need to make more ATP, so the calories will go into fat. And so that was the theory for 100 years. And our group discovered that the way it works is kind of a trick. The body actually produces, when you activate the switch, the body makes very little ATP. It drops how much ATP it makes. And so there's this alarm signal that we don't have enough energy. And that alarm signal makes us want to eat more. But the switch prevents the ATP from being made. And so that when you eat, the energy goes into fat, which is like stored energy. Fat's like stored energy. So the trick is you create a low energy state, which makes you tired and hungry. And that is what triggers food intake. And so what's really cool is that it's driven by carbs. The process that activates the switch is driven by a particular carbohydrate called fructose. But that fructose comes from sugar. So sugar is the main source, high fructose corn syrup, the fructose in the high fructose corn syrup. Sweets are the main source that activate the switch. But we can also make fructose from things like bread and rice, and cereal and chips, potato chips. So even though potato chips don't have sugar, when you eat them, you make fructose. So the trick is that fructose is the key nutrient that activates the switch, and it works by causing damage to those factories. It damages the factories so that they don't make ATP. And initially, it's a temporary one. It's kind of a temporary damage, and then the factories recover, and then they make fine ATP. And so when you're drinking sugar and soft drinks and stuff like that, everything's very reversible, and you don't have to worry. It's very easy to lose weight when it's first happening. When you start gaining weight, it's very easy because the factories are pretty healthy. They're suppressed when you're eating sugar, but then they come back. But over time, the continued attack on these factories that make our energy leads to a loss of the factories. There's actually a reduction in those mitochondria, and that's associated with disease and aging and all these bad things. So you lose mitochondria with aging, but it's accelerated by these foods. And in fact, there's this thought that maybe the mitochondria wouldn't be damaged at all if you could, modify our food intake so that we weren't damaging the mitochondria all the time. And so we've knocked out this pathway, and animals live longer. And even if they're not eating sugar, they live longer because you can produce sugar in your body. As I mentioned, you can produce fructose. So it turns out to be a really important pathway. And our group started studying it in nature, and we studied it in evolution, and we realized it's a basic process. Getting fat is a normal process for many animals, and they do it to protect themselves during times when food is not around. And but we have been able to get sugar 24/7, and we have food access all the time. So when we activate the switch and we're hungry, we just keep eating more and more, and we get fatter and fatter. Now, it isn't just from eating too, because when you activate the switch, it works independently of calories as well. So the calories help drive weight gain. But even if you were on a caloric restriction, inside your liver would get fatty. You'd start building up fat. You become pre-diabetic, your blood pressure would go up, all these things to kind of protect you from starvation, but not good when you have it chronically because it can lead to diabetes, fatty liver, kidney disease, high blood pressure, and so forth. So the switch turns out to be really important. It's driving most of the metabolic diseases. There are people trying to find ways to block this pathway. Pfizer and Lilly started programs to try to develop drugs. If we can get a drug that blocks this pathway, it will probably be more powerful than Ozempic and semaglutide and all these other drugs, which kind of look like they're working partly on this pathway. But if we actually block the whole pathway, we will block the development of type 2 diabetes. We'll save millions of lives. And so, it's a big goal is to find a way to block this pathway. In the meantime, we can do really good things to reduce our risk by, eating wisely and low carb diets, intermittent fasting. All these things seem to work through this pathway. So there's a lot to be gained here. And so by knowing the pathway and also there's new supplements, new sugars. There's even a new sugar that's out that looks like it counters this effect. So there's ways to beat this without drugs, for sure.
And when you talk about this new sugar, is that allulose?
Yes. And I do have a disclosure. I have been a researcher all my career. I spent 40 years getting funding from the National Institute of Health. I've published hundreds and hundreds of papers. I'm a scientist, and I've tried to be as ethical as I can in all the conduct I do. But I have joined a company called RX Sugar as their science officer, part-time job. And these guys produce allulose. And allulose is this sugar that looks like fructose, but does not activate this switch. And the reason I joined the company was because I'm very curious about this sugar that seems to be beneficial. And so when I talk about it, recognize that I'm the science officer, but I'm going to tell you all the good and the bad about it. If you ask me, I'm quite happy to share everything about allulose.
If you're enjoying this episode, take a second and let me know by clicking like and subscribe below. Thank you so much, and now back to the show. Well, you touched on the fact earlier that drugs like Ozempic are potentially, it sounds like there's at least a little bit of a good effect when it comes to the switch and what we've been talking about.
Yes.
The way I understand allulose, it acts like a GLP-1 agonist in a more subtle way than Ozempic. Is that correct?
Yes. So to get back, so there was this discovery years ago that there's a hormone produced in the body that no one really knew about, and it's called glucagon-like peptide 1, or GLP-1. And when they discovered this, they found that when people eat, that this hormone is released and that it helps to provide some satiety, meaning that it makes you feel full, and it helps lower blood glucose in part by stimulating insulin and through other non-insulin dependent ways. And so when it was first discovered, it was thought, oh my gosh, these GLP-1 might be another way to help diabetes because it can lower blood glucose. So a number of companies developed drugs that stimulate GLP-1 as a way to help treat diabetes. And so these drugs came out, and one of them was called semaglutide. And this drug was found to help people with diabetes. And then Novo Nordisk, who owned that drug, had this kind of interesting finding that if they gave high doses of it, that it actually could cause such satiety that people actually reduced their food intake. And they started seeing really dramatic weight loss. And I remember when the guys from Novo Nordisk came to visit me and showed me this data, I go, my gosh, this is very impressive. I mean, people were losing, 40 pounds, so easily. And so this drug, that when they found this, then suddenly everyone starts to make GLP-1 agonists. These are drugs that stimulate GLP-1. They actually don't stimulate the endogenous production of it, or they don't stimulate the hormone itself. They kind of replicate. They're kind of a mimic of GLP-1. So they're like taking a large dose of GLP-1 and they've been manipulated in a way that the GLP-1 levels are high for 24 hours a day. And so when that happens, the stomach slows down. It can't empty as well. You get full very easily, and people lose weight dramatically. And so there are all these papers that came out showing 30-40% weight loss, and it's now become the drug of the century. And Lilly's and Novo Nordisk have become some of the biggest companies in the world because of the sales of these drugs. And everyone who's having trouble losing weight hears about this, and many people want to go on it. And it can be dramatic. It's being associated with less cardiovascular events, with improvement in kidney function. I mean, it really looks good. But there's a dark side. The dark side is that it's super expensive. Not everyone can get it. And it's associated with lots of side effects. This stomach bloating and burping and belching and diarrhea. Some people have even more severe side effects, but it's very common for 15 or 20% not to tolerate it from the get-go. And over a year, maybe 40, 50% may drop out because of the side effects. So it's not a panacea. It's not a cure. It's got a lot of issues with it. And there's another issue. And the biggest issue is that when you stop it, people gain weight. Everyone gains weight back. And they can gain quite a lot of their weight back within 6 months. So this is good for drug companies because that means you have to be on this drug forever. It's not good for world health to have such an expensive drug that very few people can afford. And when insurance companies pay, they'll get you back by increasing their insurance premiums. So it's not a great thing, but it is a great thing, but it's not totally great. What's really cool about allulose, which is why I love this sugar, is, most low-calorie sugars are neutral or negative. What I mean by that is, yes, they don't activate the switch. There's a few that do. There's a few low-calorie sugars that are really dangerous, like sorbitol, which is put in syrups, tagatose. There's some sugars that you really don't want to ingest because they'll actually activate the switch in a delayed way. But most low-calorie sugars don't activate the switch, so they all have that advantage over sugar. But some of them are like aspartame can be associated with like memory loss, and saccharin can be associated with bladder tumors, and there's enough concerns that people try to say, hey, you should avoid low-calorie sugars and just tough it out. But people love sweets, and so there's this problem, and it's like wired. So what's neat about allulose is it's sweet, but it's not as sweet as sugar. And it looks like fructose, but it doesn't activate the switch. But what's cool about it is that it stimulates GLP-1, the actual hormone that in our body. So it does it like 5 to 10-fold better than most other, carbs. And so it's actually really raises the levels. And so people have noticed that it stimulates satiety, and there's a lot of clinics where they're using this to help people reduce weight regain following stopping Ozempic, for example. And I was just on another podcast with a doctor who's doing that regularly. While it can reduce weight regain, and it's been shown in clinical trials to cause weight loss, it's much milder than semaglutide. I doubt you're going to get huge weight loss with eating a chocolate allulose bar a day. But if you ate one with every meal, you might actually see some significant weight loss, and certainly it improves blood sugar. So it has that same GLP-1 effect where it really can reduce blood sugar. I have a CGM, which I'm not diabetic, but the people from Levels graciously gave it to me so I can monitor my glucose levels when I eat. And it is very, very, very noticeable that the allulose can block that postprandial rise in glucose. It's really fantastic. And we've linked that with things like Alzheimer's and other diseases. And so I think it's really good. In fact, we have, there's a guy who's got type 1 diabetes who is also a scientist, and he started taking this allulose and found that he could reduce his insulin requirements. So we've actually just submitted a case report on that, and I hope to do a clinical trial sometime. So there's some really good things with allulose, but because it's a GLP-1 stimulant, if you ate a lot of it, you might get a little bloating and belching, sort of like semaglutide. Occasionally people will get diarrhea. Some people just don't like it, maybe either for taste or they don't feel perfect with it. But most people like it and don't have side effects. So it's more than tolerate. Most people actually like it. But it's been available for a few years in the markets, and there's quite a few companies that make allulose. I recommend just checking it out. Don't have to buy the ARC sugar product, but there are a lot of foods that have allulose added. I would just check it out, see how you react to it, and if you're insulin resistant or pre-diabetic, I think it might really be a benefit. If you want to lose weight, I think it will be an assistant to losing weight, but by itself, I doubt it will be like semaglutide. But we do have occasional reports of people getting significant weight reduction, but I wouldn't bet on it solely as replacing semaglutide, because it's just it increases the GLP-1, but not at the high levels and 24-hour levels.
Do you have any idea what the half-life of allulose is compared to the 24-hour of something like Ozempic?
Yeah, it seems to be for about 2 hours after you eat it. So what's fantastic is if you eat it, for example, like if you ate it before a meal, right before, it might actually affect in that meal, make you feel full a little bit early. If you take it after a meal, you may have some benefits, but by the time you're eating the next meal, your GLP-1 is going to be back to normal. So if you're using it for weight loss, it makes sense to take it before the meal, and it may actually dampen how much you eat. If you're taking it for blood sugar and like the rise in glucose, which I think is a very serious problem, you can actually take it even after a meal. It's so fast that it works very quickly. And it doesn't cause hypoglycemia. It just kind of prevents the rise in glucose.
So there's actually two different mechanisms then. It's helping with keep us full longer, and it's keeping blood sugar tame.
Yeah.
You mentioned your CGM. So if you have carbohydrates and then you have some of that mixed in that meal,
yes,
it's going to dampen the spike. So two different pluses potentially for people.
Right. And in animals, there's data showing that it improves exercise tolerance. Like in animals that are running, if you take two groups of mice and you exercise train one group, they're going to outperform the other guys. There's the benefits of exercise training. So this group did this, and they also broke up each group by giving them allulose. And if you give allulose, you get an additional benefit in the exercise group where they can go even a little further. And it's probably because it stimulates glycogen in liver and muscle, especially in liver. And when you're running, you're burning the glucose. And if you have more glycogen stores, you can, even if it's in the liver, some of that gets to the muscle. And so it's sort of interesting. So in laboratory animals, it's also been shown to, for example, stimulate the burning of fat and reducing the fat in the liver. So there's all these other benefits, but those have not been really shown in humans yet. But we do know for a fact that it lowers blood glucose in humans. Multiple studies. It is very apparent if you do have insulin resistance and your hemoglobin A1C is high, it's something you might want to consider doing. It's not indicated, it's not FDA approved for this kind of thing because it's a food and it's generally regarded as safe. But it does have this benefit for sure. And if you have a CGM, you can test yourself. Give yourself a carb meal and then do the same exact meal with allulose, and you'll be surprised. It's very impressive.
I've been hearing a lot about its GLP-1 agonist effect. I didn't know it dampened blood sugar spikes as well.
I think between you and me, I think that's the total winner for the allulose. The glucose effects are incredible. We think that postprandial rises postprandial means after dinner, the rise in blood glucose after a meal. I think that is one of the most dangerous things because if it gets high, it can activate the production of fructose. It basically is pre-diabetes and it can go to diabetes. We think that is actually a major risk factor for Alzheimer's. And I think that the dampening of the postprandial glucose is the most clear absolute benefit of allulose that I see. The effects on weight are probably significant, and it stimulates GLP-1. I think yesterday I was impressed. Charles Cabo, who's a physician that runs a huge obesity program in Connecticut, he has hundreds and hundreds of patients. He is convinced that it's very beneficial, and he has all these testimonials that he has. So I'm sure that there's benefit there too, and maybe it's even more than I know. But the glucose effect is extremely easy to show.
For somebody tuning in who's, say, mild to moderate insulin resistance, they're metabolically headed towards type 2 diabetes, and we wanted to makeshift them together a plan to give allulose a good go. We know it lasts about a couple hours in the body. How would you go about using that? I'm assuming you could mix it in water, but what dosage wise, how much do we need to have a significant effect? And when would you take it before you were eating?
10 grams, like a chocolate bar. So 10 grams with a meal. Might be a little more effective if you gave it before, but it's going to be effective after. You'll see a very significant effect. 10 grams. And 10 grams is extremely well tolerated, especially if it's given with food. So 10 grams with each meal. The danger when you're pre-diabetic is not so much between meals as it is with a meal. So what happens is that spike in blood glucose that goes up after you eat. That is sort of the pre-diabetes. And then over time, you're right, the fasting glucose creeps up. But the real danger is those big peaks, and that's driven by food intake. So I wouldn't take allulose between meals. I don't think you need to.
When I was saying between meals, I was meaning in preparation for eating.
Oh, yeah, like properly. Well, if you did it right before a meal or like in the beginning of a meal, it might have a little bit more potent effect than at the end. But we see it even at the end. So if you like that chocolate at the end of the meal, do it that way. It works. It works beautifully. And test yourself. But again, I want to caution that this is a food. It's not FDA approved to be a treatment. And so but it is metabolically healthy and it has these effects. And there are nutrients. There's supplements like berberine, which a lot of people will say is good for insulin resistance. I've never seen anything as powerful as allulose.
I want to come back to our story of the switch.
Yes.
Fructose goes to the mitochondria, tampers with those, and negatively impacts them so they're producing less ATP. I want to try and tie this to the GLP-1 agonist.
Yes.
Whether it be Ozempic or allulose.
Yes.
Is there a fit between the two of those?
Yes, there is. So here's the scoop. If you read about GLP-1 agonists, you'll see that no one seems to really know how they work. They're working better than, it isn't just the blocking of the stomach from emptying. Initially they said, well, it's because they slow the stomach from emptying your food. So it's basically just making you full. But now they can see all these additional benefits like on cardiovascular disease and everything. And so people are saying, well, maybe it's working through the brain and it might be affecting brain effects. And one of the things that has also been identified is that there's a hormone called glucagon. Now, glucagon is kind of the opposite of insulin. And it tends, when you give glucagon, it makes glucose go up in the blood. And so glucagon is actually a bad guy, although glucagon-like peptide, GLP-1, is thought to be a good guy. So they both have glucagon in their names, so it's a very confusing thing. But glucagon itself is like the opposite of insulin. It makes blood glucose go up. And GLP-1 agents have been found to inhibit glucagon. And that may be how allulose might be working as well. And so it keeps the glucose from going up in the blood. But one of the things about GLP-1s is there was a beautiful study that shows that it suppresses the switch. And the switch is driven by a particular enzyme in fructose metabolism. And that is really inhibited big time, or the expression is reduced. So it really knocks it down by GLP-1. So I believe that there's an interaction between GLP-1 and the switch, but it dampens the switch. It doesn't turn it off. And so there is this connection. And I think that, the switch has been shown to stimulate glucagon, for example. The switch activates glucagon. It's being suppressed. So I think the GLP-1 agents are interfering with the switch, and they're getting this great benefit. But I think there'll be a day where we turn off the switch, and it will be a huge benefit, and hopefully without those side effects.
Let's take this switch story even further. Again, to recap, we have fructose coming in through the diet, affecting the mitochondria in the cell,
right,
producing less ATP.
Right.
Take it from there. What happens next?
Yes. So when the ATP levels are dropped, there's also the generation of a substance called uric acid. Uric acid is the great amplifier, and it actually recruits. This is kind of getting deep now, but it brings in an enzyme. It moves an enzyme that's normally in the cell, but not in the factories. And it moves that enzyme into the factories. And that enzyme produces bad things called oxidants. And you've heard of antioxidants as being healthy, right? They block what's called oxidative stress. They block oxidants. And this thing makes oxidants. And so when fructose generates that uric acid, it brings this machine, this enzyme that produces these really bad things into the factories, and it suppresses the factories. And the factories are making ATP a variety of ways. They're burning fat. They're producing energy from carb breakdown products. And these oxidants just go into every system. And they also block enzymes that are rescue enzymes to make ATP when the ATP levels are low. There's even a rescue system, and it suppresses that. It suppresses it 5 places. That's it, 5 places. We identified all 5. And so it turns the factories off. Not completely. The factories are still making some energy. And there's another system that takes over. There's a system where there's this old ancient system that anaerobic, bacteria use that don't have mitochondria. And this system generates ATP in the absence of oxygen. So the mitochondria use oxygen, and this other system gets turned on, and that's the system that drives cancer. So when you activate this pathway, you block the production of energy from the mitochondria from the factories, but there is this other system that takes over, which cancers love, because cancers often grow in areas with low oxygen. And now here's this energy being made in the absence of oxygen, so tumor cells love it. And we actually showed that cancer cells love sugar. Others have shown that if you feed sugar to animals with cancer, it can stimulate metastases, for Christ's sake. So it's like bad news to eat a lot of sugar when you have cancer. Now, if someone's listening, and let's say that you have a ton of cancer and you're, and they can't get rid of it, eat ice cream. If you want to eat ice cream, eat sugar, because it's not really. But if they're trying to cure you of your cancer, cut back on sugar too, because sugar is a stimulus for cancer growth. And it's been shown multiple times. So, if it's your last days, eat what you want, don't worry. But if you're trying to cure yourself of a cancer, cut out the sugar. So anyway, these factories are suppressed, and you don't need as much oxygen. That's actually a survival benefit, right? Like they're these little like gopher-like animals that live in Africa, and they burrow into these holes. They're called naked mole rats, and they can live in these under the ground where there's almost no oxygen, and they live by making fructose, because the fructose suppresses the need for oxygen, turns off the factories, and stimulates this ancient system so they can live under there. And so it turns out that it can be a survival mechanism. If you're a naked mole rat, you want to suppress your factories when you burrow, because otherwise you're going to die, because if you're dependent on oxygen, you're not going to live down there very long. And so there's what's beneficial in nature can be really bad. That's why I wrote this book called Nature Wants Us to Be Fat. And it really talks about how this switch was supposed to be a survival switch and how we've turned it into this horrible thing that's driving our disease today.
All right, to make sure I have this correct, you have fructose coming into the mitochondria, dampening ATP production, and you're going to create uric acid.
Yeah.
You're going to create oxidative stress within the mitochondria.
That's it.
It's going to revert back to fermentation to produce energy over time.
Right.
So you mentioned cancer, would that be the earliest stage of cancer, at least one mechanism for it?
It really makes cancer cells grow very, very well. And so this system, if you like take a cancer cell and you put fructose on it, it will grow like mad. Most cancers, and pancreatic, breast, there's lots of them, glioblastomas. These have all been shown to be like fructose dependent. And the cancer cells will express proteins to help take up fructose. So yes, it helps them grow. Does it actually cause cancer? That's a bigger question. The data that I've seen shows that it stimulates their growth, but it doesn't necessarily cause cancer. Do you see what I'm saying?
Yeah, and this is what I was getting at, because you're talking about two different things here.
Right.
Facilitating their growth, that fructose is going to be a great fuel if you already have cancer. But I'm coming at it from the oxidative stress, damaging the mitochondria, reverting back to fermentation. And then is that healthy cell at that point, because of fructose as the catalyst at the very beginning, turning cancerous on us because of that?
It's quite possible. There are investigators that are writing that this may be a mechanism. It is known, for example, that it's like if you have pneumonia and you get a scarred lung, that you have an increase for developing cancers in the scar. It's also been shown in pancreatitis. If you get pancreatitis and you have chronic pancreatic damage, that's a risk factor for cancer. And it's known that when you have injured regions, that cancers can develop. Interestingly, in these injured regions, there's low oxygen because there's not as much blood. And it's been shown that fructose is being produced there to help, quote, the cells live in a low oxygen state. So it's quite possible that the link is more than just stimulating cancer growth, but could potentially even cause cancer. But we have to be careful, because things that look logical need to still be proven. As a scientist, there are many times that things look very obvious, and you see an association, and then it turns out to be not true. What was that famous movie with the two kids that go down to Louisiana, and there's this thought that they killed someone because they had a car that looked almost exactly like the car of the two people that killed the individual, and then finally in court, they were able to prove that they were not the kids, even though it looks like all the world like they were. And so you have to be careful. You need to prove it carefully. You can't just make the assumption. But it's true. There's a nice story that fructose could cause cancer.
All right. I want to take this story again even further.
Okay.
We're at the point where the mitochondria are damaged. They're not producing ATP the way they normally would. They've gone to fermentation. Somebody who's tuned into this point might be saying to themselves, this is supposed to be a fat-producing switch. We're talking about producing less energy. How come I'm getting fat when all this goes awry? So talk about that piece.
Yes. So in process with the drop in fat with the drop in ATP, I said it wrong. In association with the drop in ATP and the oxidative stress, there's activations of a variety of things. One of them is the development of insulin resistance. And this has been clearly shown to be also driven by that oxidative stress. And when insulin levels start going up, they actually help store dry fat storage in the adipocyte. And that's been shown by, it's kind of the thesis that Ben Bickman and Gary Taubes and many other, Ludwig, they all point out that the dangers of insulin resistance is the stimulation of fat. And actually, we can show that this oxidative stress, for example, can also raise blood pressure, that this can activate a variety of systems that lead to fatty liver, lead to high blood pressure, and even in the brain to neurologic disease. So the low ATP state actually is sort of an alarm signal that says, hey, I'm hungry, I got to eat more. It's working in the hypothalamus and other sites. And so there's this big process to kind of, the organism feels endangered. So it wants to put on fast storage. It wants to raise its blood pressure to protect its circulation. It increases its pressure in the kidneys, which can cause kidney disease long-term, but helps facilitate excretion. It holds on to salt. It does all these things that animals might want to do when they're stressed. And if you take someone who's overweight or obese and you biopsy their liver or their muscle, you'll show that the ATP levels are low in people with obesity, even though officially they're in a high energy state. Because if you view energy as the combination of ATP plus stored fat, when you're fat, the stored fat is a lot of energy, but you're just not using it. The ATP is your active energy, and it's low. But your total energy, if you combine the stored fat with the ATP, is high. So what's really interesting is officially, people who are overweight are high energy individuals. It's just all the energy is in their fat, and their active energy is low. And the active energy is why when that's low, that's why they're fatigued. That's why their muscles, they don't want to move as much. Their resting metabolism is low. And so it's a trick, right? It's a trick. You're increasing your energy in the whole body because the body has tricked you into thinking that you're in a low energy state, and you are in a low energy state. So you eat more, but the energy you're eating is going to the wrong place. It's going to the stored energy. Eventually, it will bring the ATP levels up. So initially, when you eat fructose, the ATP levels fall, but then you eat, and most of the calories are going into fat. But eventually, the ATP levels come back up to normal, and then you're kind of reset with a higher fat store and back to that normal ATP. And then you eat fructose again, the ATP falls. You eat more, the fat goes up a little bit, but eventually the ATP goes up and you're back. But then eventually the mitochondria get damaged and your ATP levels don't come back up. Now you're locked in to a low energy state. And then it's much harder to lose weight and keep it off. But you can and keep it off if you can stimulate those mitochondria. And the main way people do that is with exercise. And so you'll see all this emphasis on the importance of exercise, that it's more than just making the muscles stronger and better. It actually can help stimulate mitochondria. And also, as you increase your muscle mass, that will also increase the amount of food you can eat, because to stay in balance, it correlates a lot with the muscle mass, which is interesting.
Is there a point of no return, though? If somebody has been overweight for a long period of time, their mitochondria have been taking hits over the years. Exercise is a piece of this to help regenerate those. But if somebody's been pushing it, is there hope?
Yeah, there is hope. And in fact, that hope is coming out soon. There's a new supplement that's coming out in a few months. That's a very high quality epicatechin. This is the supplement that's in dark chocolate. And, when people have known for a long time that there's something good about dark chocolate, and it's like in cocoa and stuff. and this is a flavanol, but it's sort of like the one in green tea, but it's a lot more potent, and it stimulates mitochondria to grow back. And this company has also approached me, and I've done research on epicatechin in the past, and I'm convinced it's a really good nutrient. So, but epicatechin is really something that can stimulate mitochondria too. So, vitamin C does a little bit as well. That's inexpensive. And so vitamin C is also good, but there's other supplements that might be good. There's probably heard of a lot of these, luteolin, quercetin, some of these lower uric acid. But I think that all these have some benefits, and epicatechin is the one that's really linked with stimulating mitochondria. I know that the group that is generating this is going to go for this great X Prize, try to show how you can slow aging within 3 years. And it's because they believe this agent might actually have that kind of improvement. There'll probably be clinical trials on it. So one way is to get involved in a clinical trial with it. But
just so we can keep an eye out for it, what's the name of the product that's going to be coming out?
Well, I don't know what the name of it is actually in terms of the but what it is epicatechin, EPICATECHIN, epicatechin. And there may be places you can buy it now, but I don't know how good the quality is. But this company is called Blue Oak. I think they're going to come out with it in the next couple months.
Okay. Will this be, you mentioned a clinical trial, will this be a supplement, a pharmaceutical?
It's coming out as a nutraceutical. So I think it's not coming out with any specific claim, but I do know they want to do clinical trials. They're asking me to be involved with them to identify, how to do it, to help them with designing it. I've given it to people with metabolic syndrome, and it improves triglycerides acutely. I think that it has some real benefits. It's been given to people with heart failure, and it improves their ability to walk. It's been given to people with muscular dystrophy, and it's helped muscle growth. I think that it needs to be tested in a clinical trial, I think, but it's from dark chocolate. You don't have to buy it. If you want, you can just get really good quality dark chocolate and eat a bar of it. There's a fair amount of epicatechin in that.
Get one that's sweetened with allulose. You can hit it from both ends.
That would be good, actually.
Have you heard of urolithin A? I know this is a supplement. I believe it's related to mitochondria.
Yes.
I know there's a product called MitoPure. It might have urolithin A. This isn't my area of expertise. I haven't played with these.
Yeah.
But
I like urolithin A. Yeah, it's from pomegranates. I always knew pomegranates were wonderful, but they actually contain urolithin A. It also stimulates mitochondria. It's another great one. You can buy that as a supplement. I like that one a lot.
Talk about the exercise piece. You mentioned putting on muscle, but for somebody that wants to use that as a tool to help rebuild the mitochondria, what would you recommend? What types? How much? And are we talking about fixing mitochondria? Or are we talking about building new ones, enhancing the ones we have? Just want to get into the nuances there.
Well, there's a guy named Inigo San Millan, who's been a coach for like Tour de France and so forth. And for years, he's been on the bandwagon trying to identify what type of exercise is best for stimulating mitochondria. And what's interesting is it's really like phase 2 exercise where you're walking or biking at a level where you can still talk, but it's a little difficult to talk. And when you get to that level, you're kind of right on the edge of making lactate. And once the lactate levels start accumulating, I mean, we're making lactate all the time, right? But once it starts to go up in the blood, it's kind of over. And so that cusp, that level where the lactate is a little increases a little bit, but it doesn't go sky high. That is the cusp for stimulating mitochondria, and so typically you have to do it like 40 minutes, 30 to 40 minutes. It's unfortunate you can't just do 10 minutes, but I think people sometimes say an hour, hour and 15 minutes, I've heard. But somewhere between 30 and 75 minutes, and I would probably say 45 to an hour, 3 times a week, is a good exercise to really stimulate mitochondria. It's been shown clinically. There are ways to assess mitochondria indirectly through various types of tests. The easiest one might be this lactate measurement, and at some point there's going to be a continuous lactate monitor, so that will really help. But at this point, I would just say, this kind of exercise like biking or walking briskly or jogging slowly, these are great exercises for the mitochondria. That doesn't mean that you don't want to also do strength training. Increase in muscle mass has been shown to be very beneficial for metabolic health as well. And one really interesting finding is that when at some point you'll find that you have to like kind of reduce what you were eating as a kid. If you eat the same amount as a kid, you're going to be gaining weight, and this is related to the mitochondrial loss, but it's also partly related to muscle loss. And what we found is that the switch actually reduces muscle and increases fat. And so muscle wasting is very common as we get older. And when the muscle goes down, you can gain weight much easier when you have low muscle mass. But when you have a high muscle mass, you can eat a lot more without gaining weight. So it really makes sense to have a good muscle mass, not only for the strength and being able to avoid falls and all those things, but it also allows you a little bit more latitude with how much you want to eat. And so strength training is really great for many, many reasons. But one reason is that, you'll be able to eat more if you have more muscle mass, and you'll be healthier and have less chances of getting into trouble falling or this or that. But for mitochondria, the best thing is this is really, like biking or walking, not so much strength training.
We've made it really clear to this point. Fructose is the big enemy here.
I think it is.
What are the top ways people here in the West are taking that in?
The number one way to get into trouble is to eat a lot of processed foods that contain sugar and salt and all these things, high fructose corn syrup. Processed foods often will have a fair amount of high fructose corn syrup in it to really make it taste better. Caramel corn and things like this, or processed foods where they've inject things into the foods to make it taste better. So processed foods is the number one culprit. And soft drinks and power drinks that are rich in sugar are bad, okay? So those are your big ones. High sugar products. I love ice cream, but don't eat a lot of it, right? Unless you eat a low carb ice cream. This Breyers, for example, has a beautiful low carb ice cream. And then high glycemic foods like French fries and potato chips, especially when they're salted. We find that the salt actually triggers the switch a little bit easier. And there's a biochemical pathway, but I'm not going to bore you with it. But basically, salty foods filled with sugar and grease are going to get you into trouble. It's not the salt so much as getting thirsty. When you get real thirsty, this triggers the switch. So if you eat salty food with and drink a lot of water with it, so that you're not thirsty, the salt's not so dangerous. So we've done studies to show that it's when the salt concentration goes up in the blood. But if you eat salt with a lot of water, it's not quite the same. But anyway, I would say avoid sugary foods, sweet foods. Not telling you never to eat a cake, but you do it in moderation, or if you're like on a low carb diet, you follow that low carb diet or that keto diet. But those diets are very effective. Intermittent fasting is pretty good. And if you don't want to do that, and just be wise at each meal, just when it comes to the carbs, just eat a smaller portion. Big pile of potatoes, just ask for half of it. If you got to have a birthday cake, try to eat a smaller slice. Eat it slowly if you can. It's very hard because it's the concentration of fructose that hits the liver that's important. So if you take a thin slice of cake and you eat it in one bite, that's going to be more potent at activating the switch than if you took 15 minutes to eat the cake. And you're talking to people and drinking your coffee, and then take a bite and keep going. And then so there's all these tricks. I do encourage people to look at my book. It goes into a lot more detail and explains how this works. So
early in our conversation, you mentioned the fact that glucose can be converted to fructose.
Right.
And this ties into the salt piece. You mentioned a complex pathway there, but the essence I've gained from your work is that when we have quote unquote too much salt, it brings down the threshold of converting glucose to fructose.
Absolutely.
So talk about that in a general sense. Somebody who's eating, we're taking salt off the table at first, just eating a regular meal with glucose. If they're metabolically healthy, how much of that gets converted to fructose? And then we'll bring salt in and talk about how that brings that threshold down.
Yeah. So you're totally right. So probably half or so of the fructose that we are using to activate the switch comes from carbs that we convert in our body. And the big ones are bread, rice, potatoes, cereal, what we call high glycemic carbs. And when the blood glucose goes up, it's converting up to 30% of it to fructose. So we think that's one of the reasons why carbs are bad, is because some of them are being converted to fructose. And when you eat sugar, you don't need to convert it to fructose because there's fructose in sugar, but there's also glucose in the sugar, and some of that's being converted to fructose. So we've done some studies to look at how that conversion occurs. And there's an enzyme that converts the glucose to fructose, and it's activated when salt concentrations go up in the blood. And so that pathway is called the polyol pathway, but basically the salt stimulates the conversion. And when the salt concentration goes up in the blood, you can actually see evidence for activation of the switch. So we did a pretty cool study where we took people and we gave them soup where we added salt to the soup. And we found that you can kind of really mask how much salt a person's eating if you give them a kind of a creamy soup with salt in it. They can't tell how much is in there. And so we gave them a good amount of salt. And so it raised their salt concentration. And we could show activation of the switch. The blood pressure went up and all these things that are associated with the switch turned on. But if we gave the soup with water and made them drink like a liter of water with the soup, there was no activation of the switch. The blood pressure stayed normal. And we've done this now in more detail. We've done combinations of sugar and carbs with salt. And we can basically show this. So salt really makes carbs worse. And so if you ate French fries that had no salt on it, it would be very different from eating French fries with salt on it. And if any of you, and I predict that some of you have been to McDonald's or Burger King in your life, and you got to remember how good those French fries would taste. And they were drenched in oil, but they were really, had a lot of salt. And French fry, these fast food places, they add so much salt. So when you eat it, you're immediately like thirsty. And then you take your soft drink and drink that soft drink with the salt. And I mean, that's like the perfect combination to get fat, right? And so they're all working together. And then, what's interesting is once you activate the switch so that you're hungry, what really stimulates weight gain is eating fat because it's so calorie dense. So you get 9 calories per gram of fat versus like 4 grams of calories per gram of carbs. So by coating it in oil and all that, you get that fat with the carbs and the salt. So the carbs and salt activate the switch, and then the fat is like putting a lot of firewood on the fire. And you get this huge blaze as you're, knocking down those mitochondria and putting tons of calories into the fat stores. So
isn't it true as well that we have leptin resistance from fructose too?
Yeah, that's it.
And that can last for up to a couple of weeks. So we're
that's right.
Naturally going to continue to eat more. So
yeah,
more bad news to add to that situation.
Yeah. We did studies in animals, and we found that, and the main mechanism for driving the food intake, part of it is from the fall in ATP directly. But the big way is because it stimulates a thing called leptin resistance, and that makes you hungry. And what we did this really cool study in animals where we gave them fructose and we made them leptin resistant, right? So now they're hungry. We took away the fructose and then we offered them a high-fat diet. And they ate a lot more high-fat diet than a control animal, even though the fructose was gone, because the leptin resistance persisted for about 2 weeks. So this is why some of these studies that have been published in humans are kind of suspect. So if you give sugar for 2 weeks and then remove the sugar and then do a study without sugar, you have this carryover effect from the sugar. And in some of these big clinical studies, they didn't know about that.
So just so I'm clear, it sounds like the salt makes the switch more trigger happy. So it happens at a less of a threshold. Right. Of converting glucose to fructose. Sorry, not the switch, but converting the glucose to the fructose. But I want to make sure I'm clear on this piece. Somebody metabolically healthy having, say, a baked potato, no salt, how much glucose does that, in that case, gets converted to fructose versus somebody metabolically unhealthy? Is there a difference there?
Well, there were, back in the early 1800s, in Ireland, potatoes were like the main food, and but obesity wasn't really very common. And my belief is the reason is because carbs alone do not make a person super fat. They make you insulin resistant and diabetic and all those bad things. But the fat, once you become leptin resistant, the fat really drives huge weight gain. So if you look in like Japan, where they're not eating so much fat, they are eating things that activate the switch, though. So they get this metabolic syndrome. They have high frequencies of diabetes and hypertension, but they don't get that same level of obesity that they get over here. Although it's now beginning to change as they're eating more of a Western diet. But and I think that potatoes probably don't activate the switch as much as potatoes and salt, and other things like how much fat is present also counts, and other factors. So if a person was just eating potatoes without salt, they might actually activate the switch a little bit. Normally about 3% of the glucose gets turned to fructose, but there's now data showing that when you activate the switch, 30% gets converted. So salt's really good at activating the switch, so it probably can really amplify the effects. My guess is that if you're eating a boiled potato with other types of food, the activation of the switch is going to be much less than if you're eating 2 bags of French fries. And so not all carbs are the same. And a lot of it relates to the salt and other things. Here's another interesting thing. If you take a soft drink and you drink it really fast, you're going to get a huge concentration of fructose hitting the liver. You're going to get a big switch. So like these kids who, when they're playing tennis and they're really hot, and then they get a big thing of A&W root beer and they drink it really fast, like I did when I was in high school, and you drink that whole thing, you're going to activate the switch, right? Whereas if you take a soft drink and you just sip it over an hour, it's not going to have the same effect. We actually did that study in people with apple juice, which is like sugar. And so we either had them drink it in one big gulp or drink it over an hour. And there's a huge difference. So, this makes it complicated, right? Because if I say to you, well, apple cider's not going to be good for you, but if you just are sipping it so slowly, maybe it will just be like a calorie. But if you drink it really fast, it's going to like sizzle your mitochondria. So it's probably better just to say, avoid soft drinks, avoid apple juice. But it is interesting. The science is interesting.
One of the numbers I was fishing for, I think, was that 3%. So normally 3% of glucose will be converted to fructose. And you mentioned that goes up to 30 once the switch has been switched.
That's based upon some studies that have been published. Some of those are kind of old studies. It would be nice to do new studies to see if the numbers are still kind of lining up like that. But that is what the literature shows.
Got it. The other layer to that was somebody metabolically unhealthy. Would there be a difference there?
Yes.
Would there be less of a threshold?
Yeah.
More glucose getting converted over for somebody metabolically unhealthy.
Yes. So remember we told about uric acid being the great amplifier?
Yep.
It amplifies the injury to the mitochondria, but it also amplifies the production of fructose. And people with metabolic syndrome or metabolically unhealthy, people with insulin resistance tend to have higher uric acids. So they're likely activating more quickly too. They're activating the switch in response to foods more quickly because they had that high uric acid.
So uric acid that's made in the energy production or lack thereof, when fructose goes into the mitochondria, uric acid is made as part of that. That's going to convert more glucose to fructose and basically create a loop of reinforcement there?
Right. But salt and uric acid are kind of interesting because they need to have carbs around to be active. So if you're on a keto diet and you're not eating carbs, and and you're not generating fructose or eating fructose, you can have a high uric acid and it doesn't really do much, and you can have a high you can eat salt and you're not going to activate the switch. So if you're on a keto diet, a lot of people say, well, you're actually at risk of of volume depletion, and you should eat a little more salt. And some people will get high uric acids, and it can cause gout. But the evidence that it is the big amplifier. It's an amplifier, so you've got to have some carbs present for uric acid to really be active. At least that's the data that our work would suggest.
And when we're referring to the switch, are we talking about the specific part of the process where fructose is going into the mitochondria and breaking that?
Yeah.
Because there's different layers to this. We're talking about now the conversion of glucose to fructose. It's all part of this physiology, but when we say the switch, are we talking about fructose going into the mitochondria, breaking that, and then causing energy to be stored as fat?
When fructose is metabolized, it's actually not, the fructose is not being metabolized in the mitochondria. It's just that it generates uric acid, and the uric acid goes into the mitochondria itself, but also translocates or shifts this oxidant producing enzyme into the mitochondria. So it does activate the mitochondria, but it's not like fructose goes into the mitochondria. It's fructose generates things that do go into the mitochondria. It's almost the same, but it's not quite.
Okay.
So,
and isn't it true that fructose always, the metabolism of it begins in the liver?
It's certainly true that a lot of the bad things that fructose does are based on its effects on the liver. But fructose can be metabolized also in the intestine, where it can do some bad things. It also can make it into the circulation and it go to the pancreas, specifically to the cells that make insulin. It gets into the brain, and fructose in the brain is a big problem with behavior in neurologic disease like dementia. Fructose can get into the kidney. And one of the bad things is that when you make fructose, you can make fructose anywhere. So like when there's a low oxygen, like if you have a heart attack, fructose is made in the heart. When you get that postprandial, or you eat like a pancake and the glucose goes up in your blood, that high glucose is circulating through your brain and other things, and that can be converted to fructose there. So it's true that most of the fructose we eat doesn't get past the liver, but fructose is much more diabolical than just having effects in the liver.
Got it. We're really getting into the weeds, but this is good because I'm sorting things out for myself here too as we go. So fructose, when it's metabolized, uric acid is a piece of that, affects the mitochondria, changing the metabolism there, causing oxidative stress.
You can now start teaching. I'm going to give you a teaching degree.
Well, you're a good teacher. I'm learning as we go here. So the other thing that makes glucose convert to fructose easier is alcohol.
Right.
So talk about that process.
Yes. So alcohol also, when you drink alcohol, it accumulates in the blood, and it raises a thing called osmolality, which is the same thing salt does. And so it acts similarly to salt in its ability to trigger the conversion of glucose to fructose. And oftentimes we'll have drinks with, sugar in the drink, for example, or you'll be drinking a beer and there'll be pretzels on the table or chips. And it's not uncommon to have carbs with alcohol. And what we found in animals is that when we gave alcohol, that the alcohol acted like salt or uric acid to trigger the generation of fructose. And we even found that that liver disease from alcohol was actually dependent on fructose. So we're actually funded by the National Institute of Health to study this relationship of sugar and alcohol and fructose. And it's really interesting, if we block fructose metabolism, we can block alcoholism. So the craving for alcohol is very much similar and linked with the craving for sugar. And this has been known for decades, that people who like alcohol tend to like sugar and vice versa. So it's turning out to be an interesting science. Our big scientific publication on this is hopefully going to be published soon.
All right, to recap, we have 3 different things we've gone over that help the conversion of glucose to fructose: alcohol, uric acid, and salt.
Right.
I believe when we were talking about salt, you brought in hydration as being a way to dilute that.
Right.
But from the other way around, we can talk about hydration as a whole, blocking that conversion of glucose to fructose. We can bring it into the salt piece, but we can also talk about it on its own.
Yeah, you're totally right. Hydration will block the salt effects. We've shown that. But it actually can benefit and turn off processes. Like it can turn down glucagon. We were talking about GLP-1 agents is turning down glucagon. Hydration can do it too. So just keeping well hydrated, drinking like 8 glasses of water a day, can be really beneficial. We can dampen sugar's effects by just giving water to our animals. So the old belief that drinking a lot of water is beneficial really is true. And we need to stay well hydrated. Now, I don't want anyone to be drinking gallons and gallons of water, because you can get water intoxicated, and that can be life-threatening. So you want to stay well hydrated, but don't think that more is better. If you're well hydrated, that's good enough. Recently, it's been shown that there's a blood test that can kind of tell you your hydration state. And that's the serum sodium, or Na, and everybody gets it. But no one seems to look at it, because it's usually in the normal range. And the normal range is like 138 to 144. But at the National Institute of Health and the Aging Institute, they recently did a study, and they found that if your serum sodium is high, but still in the normal range, that it increases your risk for aging, obesity, diabetes, and all these diseases. And so it turns out that the ideal serum sodium for everybody is probably between 138 and 142. So a very simple thing you can do is to talk to your doctor, find out what your serum sodium is. And he'll say it's normal, but you want to know the number. And if you're on the higher end, like 143 or 144, you're at increased risk for developing aging and metabolic disease, and just increase your fluid intake. A good way to look at this is look at your urine after you, or while you're urinating or whatever. And if it's dark yellow, almost certainly you're not drinking enough water. If it's clear like water, you're drinking enough or too much. And if it's just got the lightest yellow tinge, that's been shown to correlate well with being well hydrated.
So given everything we've learned to this point, getting practical, we know fructose again is the enemy. We know glucose can be converted over. It would make sense to me then, low carb diet, keto diet, carnivore diet, somewhere in that realm.
They're all good.
Would be ideal for somebody who is fat right now and wanting to turn things back the other way.
Absolutely.
Talk more about the diet piece and where somebody should jump in and what you've seen work.
Keto diets, low carb diets, carnivore diets, intermittent fasting, they all will give you great benefit. Intermittent fasting is not as good as if when you do eat, you eat a lot of sugar. So you can neutralize the benefits. But they all are basically good. And they're particularly effective at causing weight loss. So if you don't want to take semaglutide for $1,000 a month, go on a keto diet. It will be a lot cheaper and will probably work just as well. Now, but it's hard to maintain those diets. So what I've done is in my book, I've put together diets that look fairly healthy for long-term maintenance. For those people who can't be carb-free or low carb. And the beauty of that is they're sort of like a Mediterranean diet, but maybe not quite as much bread. But I think those diets do work. But the biggest problem is, everybody still has cravings for sweets and so forth. So we need to come up with other solutions. And, this is where things like allulose may play a role.
How black and white is this switch? So somebody who's taking in low carb, they're taking in a little bit of glucose. Again, we'll use that 3% number being converted to fructose.
It's a switch, but it's a dimmer switch.
Is it? Yeah. Dimmer. Talk about the continuum.
It's a dimmer. There's different levels of it. You can knock down ATP quite significantly, and that's like hitting a nail with a hammer, really hard. And you can also, have a very mild activation. And so it's not a on-off switch. It's more of a little bit more continuous. I know that doesn't sound as appealing. You'd like it to be on or off. I was hoping it was on or off, but it's really is a transition, and it sort of relates to the ATP levels. So what happens is, if you think of the ATP like a gas tank and full is to the top, when it starts dropping, it can drop down up to 40%, right? The effects are stronger the lower it goes. But interestingly, there is this rescue system where if the ATP levels go down to life-threatening low levels, another system comes on and turns off the fructose system. So instead of storing, you start burning what you have. So there is a true starvation mechanism where if the ATP levels get down to like 20%, a whole new system comes on that overrides the fructose system. You don't want to go there, though, right? That is seriously ill. But there is a rescue system. So the way we stimulate fat is to drop the ATPs to a level that's scary but not life-threatening. When it goes to life-threatening, other systems turn on to burn everything you've got to make energy to stay alive.
One area I want to make sure we have time to dig into is Alzheimer's. And this is something you've been talking about more in the last couple of years since we last talked.
Right.
And you've done some work with Dr. Bredesen, Dr. Perlmutter, previous guests of the show. Talk about this hypothesis related to what we've been talking about and the work you've done to this point and how it ties into dementia. Well,
it's been known for a long time that Alzheimer's is actually increasing. It's a metabolic disease. It's associated with diabetes and obesity. And so we've known that there's this link. We've known that just as diabetes and obesity are increasing, so is Alzheimer's. So it used to be thought Alzheimer's was something completely different. But now it's being recognized more and more as a metabolic disease. And it's associated with these special things called amyloid plaques. So people have been focused on that. But it's also associated with insulin resistance in the brain. So a lot of people call it brain diabetes. And in previous years, people are now trying to treat it, for example, like by giving intranasal insulin and things like that. So there is this recognition that some of the earliest changes in Alzheimer's are associated with insulin resistance and with a reduction in ATP production in the brain and with suppression of the mitochondria. So it doesn't take a big jump to go, oh my gosh, that's what fructose does. And then when people start looking like in the brains of patients with Alzheimer's, they've been finding very high fructose levels, 5 to 7-fold higher than normal. And they find activation of the fructose enzymes. And they find evidence of the fructose pathway. And then if you give sugar to animals, they just, after a while, they have trouble going through a maze. And when you look in their brains, they develop insulin resistance and they get mitochondrial problems. They don't make enough ATP. And it affects exactly those sites of the brain where Alzheimer's occurs. And then, if you give sugar long enough, they start forming amyloid plaques. I tell you, also things like high salt diets and high sugar diets have also been linked with Alzheimer's. It's like a perfect fit. No one has ever found a pathway for Alzheimer's from the beginning to the end that fits. This one fits completely. The risk factors, the findings in the brain, the sites in the brain. And interestingly, there was a survival mechanism initially, because the way sugar works is when it first works on the brain, it kind of stimulates foraging. And to stimulate foraging, it makes you wander looking for things. It stimulates this kind of activity. It makes you hungry. And the way that does it is it actually turns off areas of the brain and makes those areas insulin resistant. And that actually makes, these are areas in the brain that are involved in self-control. And so by blocking that, it makes you more willing to go into dangerous places to look for food and stimulates foraging, but it's actually inhibiting the neurons in certain regions of the brain that are involved in memory and reasoning and things like that. Because if you're going to forage, you really want to be able to go into dangerous areas. And so what's happened is when people develop Alzheimer's, they develop a wandering syndrome. 6 out of 9 do, where they will wander off. And no one really understood that. Now we understand that that's actually a carryover of this foraging pathway. So I think the whole story fits. Risk factors, mechanism, evidence in humans, from the beginning to the end. And so the question is, what's actually driving it? Well, as we mentioned, when you eat fructose, a lot of the fructose we eat is taken up in the liver. But whenever that blood glucose goes up, you're producing fructose in the brain. And a group in Yale actually showed it in people that brain fructose levels go up 30 minutes after your blood glucose levels go up. So controlling blood glucose and preventing that postprandial glucose rise probably is the most important thing we can do to prevent Alzheimer's. I think it's one of the number one mechanisms. So I think that we should all be reducing the carb intakes. We should be careful with how much sugar we eat. We should stay well hydrated. If you want to try the allulose, it may be beneficial here. and so forth. I also have a little research foundation. If you look up my name, and if you have a desire to help do research on this, any money you put into that research foundation will go strictly to research 100%. And we'll be looking at, how fructose causes Alzheimer's.
Has there been any research showing reversal? Somebody that's at the stage where they've had cognitive decline, plaques in the brain.
There is one.
Apply what we're talking about today and go back the other way.
Well, Dale Bredesen believes that, he has found evidence that, initiating a very healthy diet can have benefit. GLP-1 agents have been shown to help slow dementia, maybe even reverse it a little bit. So there's some evidence that you can. And interestingly, there was a paper published about 3-4 months ago where they blocked that fructokinase, that fructose enzyme in the brain in diabetic animals that were having trouble going through a maze, and it helped them. It helped. So I do believe that if you catch this early, you can reverse it. The trouble is that by the time it presents and the brain is shrunken, because over time the brain starts to shrink, I'm not sure we can bring back the brain to normal size. That would be incredible. There may be a day we can, but we certainly can't do it now. But if we can, catch it early, so when people are beginning to develop memory problems and it's still early, consider going on a keto diet, consider cutting out carbs, consider changing all these things, consider taking allulose.
Throughout our conversation, we've talked a lot about converting glucose to fructose and some of the things that catalyze that reaction. You brought it up again when we were talking about the brain specifically in dementia, the creation of fructose within the brain. Is that different than the general conversation we've been having throughout?
No, it's really the same story. It's just that this is going on in the brain, and it's also going on in the kidney. It's probably going on in the islets of the pancreas. No, it's all one story, frankly. But it's all this, and all the same foods that can stimulate fructose in the brain will stimulate it in the liver, and et cetera, et cetera. So they all are pretty much the same. The only difference is that dietary fructose, only a small amount of diet fructose gets to the brain, but the fructose generates things that still affect the brain.
Before we part ways, I want to bring up one other diet piece, the umami foods. This is a piece of this whole puzzle here, and I want to make sure we dig into it.
So umami is the taste. It's the fifth taste. It's sometimes called the savory taste. It's delicious, right? It's gravies, the French, when they're cooking and they take that rich sauce and they keep, cooking it until it's a really rich sauce. That's usually very high in umami. The reason people love beer is because the brewer's yeast is basically umami. And so the flavor of beer has not only the alcohol, but has this great flavor that stimulates umami. So umami is, we don't eat that much umami compared to like sugar, but it's considered a very wonderful taste. But it turns out that umami is used. The reason we like umami turns out because umami foods tend to generate uric acid, and that's part of the survival pathway. And beer is really good at raising uric acid, more so than alcohol. And non-alcoholic beer has the brewer's yeast, and it raises uric acid too. So it turns out that these are foods to raise uric acid. Uric acid is the great amplifier. So we can show that uric acid can amplify the effects of other foods to cause obesity. So it's an amplifier. And so if you're not eating carbs, the umami is not going to be so powerful. But if you're eating a lot of carbs, the umami could add up. in the big picture, it's not as big a deal as sugar or carbs. But if you're eating a ton of fried shrimp, and the shrimp is very rich in umami, you may not have to eat sugar, to get fat, because the shrimp can activate the conversion of that potato or that rice to make uric acid, to make fructose, I should say.
Any other foods, common things we're doing out here in the West that are raising uric acid?
No, it turns out that there are other ways to activate the switch, like super stressful situations. Emotional stress can actually activate part of this pathway, kind of like raise uric acid levels. Exertion to the point where your muscles are breaking down. So like marathon runners, when the muscle starts breaking down, these things can all kind of like activate switches too. But they're all relatively minor. When you have a heart attack, the switch is turned on in the heart. The switch is turned on anytime there's a lot of stress. And eating a lot of salt, like a salt lick, where dairy's eating it, they use that to help them gain weight for the fall, during the fall. So the whole thing is linked with nature. And it was supposed to be good. It's just that we've learned how to keep it activated at a big level.
When it comes to the stress piece, is it more chronic stress or acute stress that's impacting that?
It's not really been studied very well. I don't know. I can predict, you and I can both predict it's probably more chronic stress, but I don't know.
All right, Rick.
All right,
Any last
Jesse.
thoughts before we part ways? Round 2 has been great. Got to get into a lot more of the nuances around this stuff and bring the dementia piece in.
Yeah.
Anything else you want to share other than we're going to link up your website, your social media, everything in the show notes, your book?
Yeah, I really appreciate that. Yeah, I appreciate that. No, that's great, Jesse.
All right. Thank you.
Thank you.
Now that you're done, you're going to want to stick around here and catch this other incredible episode. You don't want to miss it. I'll see you over there.
Once you understand where the non-science is coming from, where the propaganda is coming from, and it is industry, pharmaceutical, and religious ideology. Now I understand why I was conned in my medical education.